This review lecture will discuss Chapter 6, looking at shear stresses and beams, but also looking at nailed and glued beam connections. Chapter 6 deals with shear stresses. So we might find the maximum shear stress or the shear stress at any point by using VQ over IT. For the shear flow, typically we use a shear flow to look at the force in nails for nailed connections. This is a figure that you've already seen in the past, but anytime we have any beam, we have internally a shear force in a bending moment diagram, and that shear force results in a shear stress. So the shear stress, again, VQ over IT. The key thing to realize is the shear stress, both horizontally and vertically, in that small little element is the same. So if you're looking at nailed connections or glued connections, it doesn't really matter if you're looking at a vertical connection or a horizontal connection. Basically, the key to these problems is determining the correct Q. So the V may be given to you. It may be found by a shear and bending moment diagram, the shear bend diagram particularly. The moment of inertia is always the moment of inertia of the entire cross section, and the T is the thickness that you're looking at for a particular case. So the shear flow, again, was determined or found by doing a force balance equation with forces in the x direction, but it's basically a horizontal force over some horizontal distance, and then we got the VQ over I, and the shear stress is a force over an area. So when we put the thickness there, we get units of MPa, Newton per millimeter, force per area. Here we get newtons per millimeter, or force per unit length. So typically we saw this before, in problem 6.4 is a prime example of using this formula to find spacing. So we would find, so shear flow is force per unit length to find the force in the nails and the bolts, whereas the shear stress is forces per unit area to find the maximum stress, stress at a particular point, or stress in glued joints. So in this particular example, and I showed this exact example before, and for some reason when I go between my laptop and the tablet, these seem to get changed for some reason. Those are exponents rather than 103s. So for the glue joint or nail joint, there's two different cases. For nails, we need to use our shear flow calculation, and we calculate our Q based on the area. So we are looking at, this is our area, this is our Y bar, and we determine Q. For glue, let's say instead of nails, we take those nails out and we just put glue at those same joints. How do we look at that, and how does that differ? So for glue, you have, instead of discrete points as we do in the nails, so for the nails we should find a force per unit length, and then we have to divide that unit length. So we have a force per unit length, we multiply it by the spacing to get a force per nail, and then the shear stress in the nail would be the force over the cross-sectional area of the nail. So if we have 3 millimeter diameter nails, we have 67.2 MPa. But the case of glue, that glue goes along the entire length, so shear flow is not appropriate. What we do is shear stress directly, and the area is, again, that area that's glued. So the 19 millimeters, and then there's 2 of them. So similarly for the nails, we have 2 nails. Here we have 2 glue joints, and we find the shear stress is 166 kilopascals. So basically, for the nail, we would compare this to the allowable shear stress of nails for steel. For this, we would, shear, not normal. Normal stress allowable for glue. So in these particular cases, both these particular cases, they're well over designed as far as nail and glue joints. The member would fall apart at other places rather than the nail or the glue joints. The other type of problem we could get is we want to find the maximum shear stress. So this is a problem from your particular book. Actually, I took it from a book and I lopped off the bottom, as you can sort of see here. But my point here was to find the maximum shear stress in the cross section. So by now you know the maximum shear stress is at the neutral axis. So we have our neutral axis, and our shear stress has a distribution that basically is a parabola with the highest point at the neutral axis. And it also will depend on the thickness. So you may have here is very small and then it jumps sort of like that. So in this particular case, again, you might have two different parts. For example, finding the moment of inertia could be a mini problem, but ideally finding the Q. This would be an interesting problem because Q is the important part here. So we can see in this particular case, we want to find the maximum shear stress. So the Q is AY bar. So how do we determine that? So in your book, it says to draw a horizontal line at the point that you're interested in, and then you can take the area above that point, but ideally you can also take the area below that point. So in this particular case, we know the shear stress at that particular point, whether we take the area above or the area below, we get or should get the same number. So I just wanted to show you that quickly. So to do this comparison, let's redraw what we have. We have a T-shaped section that looks something like this. Here we have 12, 12, 75, and 125, all in millimeters. So the first step obviously is to find the neutral axis. So the neutral axis we can do as we always do, but for the sake of brevity here, we found it and it's 64.7 millimeters. So as I mentioned, we can either take the area above or below. So let's start with the top. So the top, we want the area here and the area here. So Q equals AY bar. And we have multiple pieces. It's just easier to do each of those pieces individually than finding the centroid of this now shaded in part. So we have for our top skinny part, we have A is 125 by 12 millimeters, and the Y bar for that particular case, we'll call it Y1, is 16.3 millimeters. Basically this here is 10.3 to give us our 75 and then half of 12. So AY bar, and then we have that little tiny piece we have to add on to it, which is 12 millimeters by 10.3 millimeters by the Y bar of 10.3, which is half of that, 5.15 millimeters. We add these together. Let's call them Q1 and Q2. So our total Q is, with rounding, 25,100 millimeters cubed. So for our bottom part, let's try our bottom. And what we have is now this area with this y bar. We'll call this y bar 3. We have our area. It's 12 millimeters wide, 64.7 millimeters tall, and the centroid is then obviously half of that, 32.35 millimeters. So this is y3 or y bar 3, and we get, again, with rounding, the same amount. So ideally, what I want you to get out from here is when you're doing a problem, if you're doing an exam, look at the easier part rather than the harder part. So again, this is just a brief discussion of chapter 6. I think it captures the primary parts that we're looking at, and future lectures will look at the other.